Okay, yeah, good morning, good evening, good afternoon, depending on where you are. Welcome for our sixth edition of the GRSS Young Professionals and ISPRS Summer Consortium, Student Consortium Summer School that occurred in this year in a virtual way. We welcome all participants that joined our event. And I will just start a short video from our sponsors, the Geoscience and Remote Sensing Society and the International Society of Photogrammetry and Remote Sensing Student Consortium.
Good morning, my name is Paolo Gamba and I am the president for the year 2020 of the Geoscience and Remote Sensing Society. Okay, so first of all, what is a scientific society? What is GRSS? So a scientific society is a group of scientists, researchers and practitioners with common interest and common framework for building a community. In our specific case, we are people who are dealing with theory, concept and techniques of science and engineering as they apply to remote sensing of the Earth, ocean, atmosphere and space, as well as the processing, interpretation and dissemination of this information. So what are the activities of the IEEE Geoscience and Remote Sensing Society? Well, we have a number of applications. We support conferences. We have professional activities. We have a number of information service and technical activities and education activities as well. We are a global community, which means that we are arranged around large number of groups of people that we call chapters all around the world. We have currently more than 90 chapters all around the world. As a result, GRSS disseminates premium science by means of its three main journals, which are the Transactional Geoscience and Remote Sensing, the Geoscience and Remote Sensing Letters, the IEEE Journal of Selected Topics in Applied Earth Observation and Remote Sensing, but we have also a magazine, which, by the way, has a very, very important role. We also provide opportunities for the different communities, like, for instance, the community working on image analysis and data fusion. We also sponsor community-driven events, like the very successful Earth Vision workshop, but also the SpaceNet Challenge Data challenges here, which is organized by SpaceNet. We support also community-developed tools like the DESE website, which is Data and Algorithm Standard Evaluation website, and also activities related to RFI observations. So we also facilitate and connect. We have a number of activities at in our main conference. We have the so-called TIE events, but we also organize different events related to connection with companies, industries. We have a number of activities like for young professionals, for women in engineering and in geoscience and remote sensing. And we share our knowledge on hot topics by means of distinguished lecturers and industry speakers. We have also a number of educational activities. This is one of them. This is basically, let's say, one of the many different small educational videos for kids that we have in different languages, but we have also, in addition to that, a number of webinars, which are also for people who are not kids, about remote sensing in different languages as well. We offer continuing education by means of webinars, which is especially important and useful in this situation where we are not able anymore to move around the world as we were in the past. So we can support continuing education of students and young professionals through conferences, journals, our magazine, webinars, and so on. We can promote capabilities of the different communities, algorithms, data set by means of the data fusion context, by means of dedicated events at our conferences, by means of the industrial distinguished lecture or industrial speakers. We help connect companies and young motivated people by means of the Young Professional event, by means of student grants, by means of the TIE Forum. And we make the different community of Earth observation practitioner and researcher be aware of their and your topics of interest. So GRSS is actually a community of communities where we could together share and promote ideas, systems, and data set. We can meet with other communities and gain from their perspective, and we can build different collaboration to learn more from each other's and to come together in conferences. Thank you very much, and I hope you will enjoy this summer school and all the interesting topic and talks that you are going to listen during these days.
Hi everyone, my name is Cheryl Rose Reyes, and I currently serve as the president of the International Society for Photogrammetry and Remote Sensing Student Consortium. I am very happy to welcome you all to the 6th edition of the IEEE GRSS Young Professionals and ISBRS Student Consortium Summer School this year. To start this event, I would like to present a bit about the ISBRS Student Consortium. We are the official representation of the youth to ISBRS. We link students, young researchers, and professionals worldwide interested in photogrammetry, remote sensing, and spatial information science to promote their scientific and professional developments. We advocate imaging and geospatial science for informed, scientifically valid, and technologically sound observations of Earth conditions and trends that lead to improved and effective decision-making. The consortium is also accepting registrations for individual membership. Please scan the QR code in this slide if you are interested to join us. I work together with members of the board of directors from all across the globe. Charles from Uganda is our vice president. Charmaine, who is currently in Ireland, is in charge of our newsletter. Mustafa, our social media administrator, is from Turkey. And finally, Sona from Azerbaijan is our web administrator. One of the major events that we host and coordinate every year are the summer schools. In 2019, the summer schools were in Uganda, Poland, South Korea, and Brazil. These summer schools provide international learning opportunities for students and young professionals at a minimum cost. This year, we scheduled 3 summer schools, but due to the COVID-19 situation, 2 of them were postponed, and we are sincerely thankful to the organizers of this summer school for making this an incredible virtual event. This is the first ISPRS Student Consortium Summer School that will be hosted online, and as you can see, we have an amazing lineup of speakers who will deliver lectures on remote sensing and machine learning. The consortium currently hosts the virtual rooms and the webinar series to provide our community with more opportunities to learn and interact with experts in our scientific community. The webinar series was conceptualized in 2018, and we have organized webinars on Google Earth Engine, computer vision, and machine learning. The virtual rooms is an initiative to keep the members of the consortium connected during this challenging time and to help them navigate our changing lifestyles. All the resources for the webinar series and the virtual rooms are available on our website and our YouTube channel. We also publish an official newsletter called Spectrum, which covers the broad applications of remote sensing, photogrammetry, and spatial information science, and welcomes contributors from diverse backgrounds and disciplines. We publish 4 issues a year, and our most recent issue is related to the current pandemic and the significance of geospatial information in tackling the impacts of this global health crisis to our society. The ISPRS Congress is one of the biggest gatherings in our scientific community, which is held every 4 years. The Congress hosted a virtual event for all papers submitted this year and postponed the in-person meeting for 2021. During the Congress, the consortium will be hosting a 3-day youth forum, which will feature the following activities: speed dating, technical sessions, a special session on women in remote sensing, photogrammetry, and spatial information science, a panel discussion, the General Assembly for our members, a student night, another summer school, and will co-organize a mapping party. The consortium would also like to invite you to nominate papers for the Excellence Award to be given during this event. Please scan the QR code for eligibility and nominations. Also, please visit the ISPRS Congress official website for updates. Finally, I would like to invite you all to join our communities on Facebook, Twitter, and to visit our website for all the information shared in this presentation. And again, I would like to invite you all to register as an individual member by scanning the QR code on the right. This is the end of my presentation, and I wish you all a meaningful summer school. Thank you very much.
Well, in the name of the GRSS Brazilian chapter, I must tremendous acknowledge Paulo Gamba. This is actually the president of the Geoscience and Remote Sensing Society. And the second talk delivered by Shelley Rose Rice, that is actually the president of the ISPRS Student Consortium. Well, I will hand now to Professor Galera Mônico from the São Paulo State University, Presidente Prudente, to conduct actually this share, or to be the chair now officially of this wonderful talk. I must also acknowledge Professor Dr. Christopher Roof, or Chris Roof, for accepting actually our invitation and for being here and sharing his knowledge and also his precious time. Professor Galera Mônico, the room is now yours. Thank you also for accepting our invitation to be the chair actually of this talk, and I will let you actually the room to present also the lecture and the other colleagues that will support you in this sharing session. Thank you a lot, Galera, and the room is now yours.
Thank you, Veraldo, for the introduction. And I'd like also to congratulate you and your team to organize this very nice summer school in Brazil. I'd like to introduce my two colleagues that will share this afternoon here in Brazil. First of all, hello everybody, good afternoon, good evening, good morning, because a lot of people from the world is taking part of this conference. You have the talk number 6, and I'd like to invite Dr. Felipe Niewiński from Federal University of Rio Grande do Sul. Felipe Niewiński is an expert on geodetic remote sensing, especially on reflectometry GNSS. And I also would like to invite Crislaine Menezes da Silva, a PhD student at UNESCO, work with multi-GNSS position and ambiguity resolution. She will share the session with me. Hello, my friends.
Hello, Professor. Thank you for the invitation. It's a great pleasure to be here today.
Yes, thank you very much you for accepting Crislaine and Felipe. Now, let's introduce our speaker of this afternoon. I'd like then to introduce Dr. Chris Roof. And also I'd like to say thank you for accepting for giving this talk. Dr. Christopher Huff is from University of Michigan, USA. And he's going to talk today about the NASA Cyclone Global Navigation Satellite System Earth Venture mission. Chris Ruff is currently a professor of atmospheric science and electrical engineer at University of Michigan. He has worked previously at Intel Corporation, High Space and Communication, at NASA JPL and Penn State University. He is the principal investigator of the NASA CYGNSS mission. Professor Ruff is a fellow of the IEEE and former editor-in-chief of the Translation Geoscience and Remote Sense. Thank you very much, Chris, and then the room is yours.
Thank you very much. I just want to check to make sure you can hear my voice. Is it okay?
Yes, here.
All right, very good. Yeah, thank you for inviting me. I'm very happy to be able to meet with you, at least virtually, and share some information about the NASA Cygnus mission that I'm the principal investigator of. I'll start by just pointing out in this picture here on the first slide, this is what the satellites look like in orbit. They're in orbit now today. There's 8 of them in a common orbit following after each other, sort of similar to the way this picture shows. And today I wanted to do several things in my description of the mission. First, a little bit of motivation about the science that we were trying to do when we initially designed the mission, and the way that the science objectives influence the engineering design of the satellite and the sensors, the remote sensing sensors on the satellite, and also the mission concept, the orbits and so on. And then I'll show you some examples of the hardware that was developed and the early on-orbit behavior of the hardware. And then I'll show you some of the scientific results that were directly related to the initial science objectives of the mission, which is studying tropical cyclones and hurricanes. And then I'll show you at the end some new science applications that we've started working on more recently that were not the original intent of the mission, but we've found a number of interesting new applications for the remote sensing measurements for other uses in addition to the hurricane science investigations. And yeah, so that's kind of an overview of the talk today. So yeah, the initial science motivation for the mission is kind of nicely summarized in these 2 first slides. These are slides that report on the quality of numerical weather forecasting by the United States National Hurricane Center. This is the part of the US government that is tasked with forecasting where hurricanes will go and how strong they will be in the future, and in particular, identifying where they will make landfall when they're coming across the Atlantic Ocean, where they will reach the coastline of the United States, and also how strong they will be as they reach the coastline. So this first plot shows the error in the forecast for the hurricane track. So hurricane track means identifying where the center of the hurricane is, the eye of the hurricane, and into the future. And this is, there's several things happening in this plot. On the x-axis, this is the year in which the hurricane forecast was made. So the National Hurricane Center keeps records of the quality of their forecasts over time to see how well they're doing. And then these different colors are forecasts a certain distance into the future. So this bottom one, the red line, is the forecast 1 day into the future, 24 hours, and then the green is 2 days or 48 hours, and so on. And what this plot shows is that the forecast for the track of the hurricane, which is where it's going to be, have steadily improved over the last 25 years from maybe 100 nautical miles. This is a 1 standard deviation error in the forecast. And more recently, the forecast error is about 1/2 of the error 25 years ago. So the quality of our ability to forecast where the storm will be and in particular where it will make landfall when it reaches land, has steadily improved by about 50%. And this is very good news. And a lot of the reason, I guess there's two primary reasons why it's gotten better. One of them is the improvement in the numerical models, and a lot of that is because of the improvement in computer capacity. You know, computers have gotten bigger and faster, and so you can use finer grid sizes in space and time to be able to more finely resolve the underlying physical dynamical variables that affect the evolution of the storm. So better computers, better forecasts. The other thing that's had a big impact on this improvement is the quality of the remote sensing measurements by satellites in particular that have gone into the initialization of these models, because there's more satellites in orbit measuring the Earth, and also better quality in the retrievals of geophysical parameters. And in particular, the geophysical parameters that are necessary to inform the forecast for where a storm is going to go are things that will affect the direction of a hurricane motion. And those are primarily environmental fields, not in the center of the storm, but around the storm, within 1,000 kilometers or so of the storm. Things like the pressure field, the surface air pressure, the temperature of the ocean, or the steering winds, the background environmental winds that would push the storm one way or another. So those sorts of variables are well measured by the types of remote sensing satellites that have been flying and that are flying more now than they were 25 years ago. And all of those things have gone into the positive impact on the quality of hurricane forecasts for track. So a similar sort of plot of this is also maintained by the National Hurricane Center to assess the quality of the intensity of a forecast. And that's what this plot is here. So hurricane intensity is a measure of the peak sustained wind. It's the maximum wind anywhere in the storm averaged over 1 minute. And this is the number that's typically used when you categorize a hurricane, whether it's a category 1, category 3, category 5. It's the peak sustained wind, or the intensity. And what these plots show, there's similar plots over time and with forecasts 1, 2, or 3 days into the future. What they show is that there's been essentially no or very little improvement in our ability to forecast how strong a storm will be tomorrow, or the day after tomorrow, or the day after that. Very little improvement in hurricane intensity forecast skill. And the probable reason why there hasn't been much improvement is because the things that will influence how strong a storm will be tomorrow or the day after tomorrow are very different than the things that will influence where it will go. You know, the things that influence where it will go are environmental fields away from the center of the storm that will steer the direction. But the intensification of a storm is primarily influenced by things happening in the center of the storm, because that's where the energy comes for the intensification. And the primary source for energy with typhoons or tropical cyclones or hurricanes is the release of latent heat in the atmosphere from evaporated water vapor. That's the primary source of energy. So what happens is the wind blows across the ocean surface, and that wind causes evaporation of water vapor from the ocean into the air. And the more wind there is, the more evaporation there is. When water evaporates, it changes state from liquid to gas. And when it changes state, it absorbs or carries a huge amount of latent heat with it, the latent heat of vaporization. And then when the water vapor rises up into the air and condenses back into a liquid and converts to a cloud and then rain, all of that latent heat is released into the atmosphere as sensible heat. And that heat that's released from the condensation of water creates wind. And that wind then creates more evaporation and a positive feedback mechanism. And that's exactly what makes hurricanes grow suddenly and rapidly, is the positive feedback mechanism between wind, evaporation, latent heat release, more wind, and that cycle. So the right way, or a good way to try to improve the forecasting of intensity, is to measure something in that cycle, that energy cycle. And in particular, if you could measure the wind speed at the surface of the hurricane, in the middle of the hurricane, you could then quantify the latent heat flux going up into the atmosphere from the evaporation and you could track the energy and track the intensification. So this has been recognized for quite some time, that if we were somehow able to measure the wind speed in the center of a hurricane, we could improve the hurricane intensity forecast. And that's a very difficult thing to do for several reasons, which I'll get into in the next few slides. So there's a number of ways that hurricanes are measured, or tropical cyclones are measured routinely from satellites. And one of the most common ways is with optical and thermal infrared imagers. And an example of that is these are GOES imagers. These are U.S. National Weather Service satellites that are operated over the equator in geostationary orbit. They have very high resolution visible infrared cameras looking down at the Earth all the time, taking pictures often every 15 minutes or so. And this is an example of an image taken by one of the GOES visible cameras of a major hurricane. And you can see, the eye right here. You can see the spiral rain bands going out from the storm and so on. So these types of measurements are very good for localizing where a storm is, and they can make frequent updates so that you can watch the storm moving. The problem with a measurement like this is what you're really seeing are the cloud tops, because visible and infrared wavelengths can't penetrate through clouds, because the wavelength, in the visible and infrared is much, much smaller than the size of a cloud drop. A suspended cloud drop is typically kind of 0.1 to 10 microns, and the wavelengths are much smaller than that. So there's a lot of absorption, a lot of scattering, and you can't see through clouds. So you're not able to, from these measurements, directly measure the wind speed at the surface under the hurricane, which is what you really want and need to improve intensity forecast. So an alternative would be to operate at a longer wavelength to be able to penetrate through the clouds and the rain, and that's done in the microwave. So spaceborne microwave observations are able to measure surface winds and also measure the rain itself, because there's some interaction with the rain. And an example of this is one picture. I think this is the NASA TRIM satellite, which has a passive microwave instrument on it. And this is an example of the precipitation that's measured. So this instrument operates at wavelengths of about 2 and 1 centimeter. So it's able to penetrate through clouds, but it has some interaction with precipitation. So it can measure the rain itself. And you can see this is the a measurement, a data product from the TRIM microwave imager of precipitation everywhere in the world. And for example, you can see the strong line of precipitation in the intertropical convergence zone near the equator going across here. And then there's some storms and some other features here and there. So this is a typical data product produced by the TMI imager on TRIM. And there's an attendant data product that's also produced by the same instrument, and that's the surface wind speed. And this is an example of that. This is surface wind speed across the globe, measured by the TMI imager. And you can see things like there's some kind of cyclonic organized storm right here, and you can see some different features with different weather patterns in the winds. So this is able to measure wind over the ocean, which is what you want. But there's two important problems with using this kind of data product specifically for assimilation into a hurricane forecast model. One of them is that because of the wavelength of operation of these microwave imagers, there's still some interaction with the precipitation, which is exactly why you're able to retrieve precipitation. But when the rain is really heavy, and raindrops are typically kind of 0.1 to 5 millimeters in size. So it's of the same order as the wavelengths of operation of these sensors in the microwave. So because of that interaction, when the rain is really heavy, you can't penetrate through the rain. The optical depth is too high, and you don't get enough sensitivity of the surface to be able to resolve the wind. And you can see that in this image here. The regions in the wind image that are black right here, these are areas that are flagged out by the algorithm with a rain flag, because the places that are black here are the same as the places here that have very high rain rates. These red precipitation levels correspond to these blacked out wind speeds. And the reason is there's too much rain, and the sensor or these microwave frequencies cannot penetrate through the rain to see the surface. So it's just not possible to measure the wind speed in these conditions. And the problem is with hurricanes and tropical cyclones, near the inner core of the storm, where all the energy exchange is happening, there's always very, very heavy rain. That's part of the whole energy cycle, with the latent heat being released and the water condensing back into rain. There's always rain. So you just can't use these kind of sensors to see wind in the center of the hurricane. So that's one problem with this type of sensor. Another problem is, it's a little more subtle, but you can sort of see it in this legend at the top here. This is a 3-day image. And what that means is there's a single satellite in orbit, in a low Earth orbit, and it takes 3 days before the orbit starts to repeat itself, as the Earth is, turning underneath the orbit plane. So you don't come back to the same place on the ground until once every 3 days, typically. And so this looks like a snapshot of the rain everywhere in the world, and this looks like a snapshot of the wind speed everywhere in the world at one time, but it really isn't. This is a composite of data taken over 3 days. So, the wind here might have been one day and the wind over here a different day, and it takes 3 days to fill the whole image in. And the problem is, when you're trying to measure something that's changing quickly, like the rapid intensification phase of a hurricane, the winds can change over a time scale of hours to 12 to 24 hours, that sort of time frame, when the rapid intensification happens. And if you're sampling once every 3 days, it's very likely that you'll either miss the signal entirely or alias it, because you're undersampling the dynamics of the change. So for these two reasons, the inability to penetrate through rain and the inability to make measurements often enough, these types of sensors are not really amenable to assimilation into forecast models. So what's done practically to get around this problem is to operate sensors at even lower microwave frequencies or longer wavelengths, so they can penetrate through the rain. The problem with doing that is, as your wavelength grows with a sensor, the requirements on the size of the aperture of the antenna also grow, because they scale linearly, and it becomes impractical to put a big enough antenna on a satellite in orbit to get the necessary spatial resolution to be able to see the small features in the inner core of the storm. So to get around that, there's microwave sensors designed to measure hurricane winds at much longer wavelengths, lower frequencies, but they're flown on airplanes instead of satellites. And this is an example of something like that. These are instruments that are flown on a fleet of airplanes that are operated by the U.S. government, by the combination of the NOAA, which is the research branch of the National Weather Service, and also the U.S. Air Force has a number of these sensors on some of their airplanes to support the needs of the civilian weather forecasting community. And these instruments, here's one of the instruments here. It's mounted on the bottom of this airplane here. It operates at C-band at frequencies between 4 and 7 gigahertz, so much longer wavelengths. So they're able to penetrate through the rain and see the surface winds in high wind conditions in a hurricane. But you have to be very low down in order to get adequate spatial resolution. And this is an example of some measurements made by one of these instruments with an airplane flying through Hurricane Katrina. So here's the hurricane here. This white line is the flight line of the airplane as it passes through. And then these are the measurements, geophysical measurements of wind speed and rain rate retrieved by this instrument as it flew through the storm. And you can see, for example, the winds get higher and higher and higher, and then they fall off right here at the edge of the eye wall. This is the center of the storm, the eye of the storm, with low winds, and then it goes back up again. And then the green line are the spiral rain bands with the intense rain that's falling in these spiraling regions here as the airplane cuts across them. So these measurements are made routinely whenever there's a storm that's coming close to the United States. They'll fly these airplanes into the storm to make these measurements, and then the measurements will be fed into the numerical forecast models to improve the forecasting. The problem is there's only a few of these airplanes. They can't fly all the time, and they can only operate when the storms are reasonably close to the United States, because they're based in the US in Florida. So what you'd really like is to have this sort of capability, but on a satellite, so that you can make measurements more often and globally. So in order to make these sort of measurements, you need to operate at a long wavelength. In order to make the measurements more often, you need to have a lot more satellites instead of just one that comes around every 3 days. And those two characteristics are really the heart of the motivation for the Cygnus design. We needed to have a remote sensing technique that can measure ocean wind at a very long wavelength so we can penetrate through the rain. And we also needed to have a technology that requires, that's small enough, low enough power, and cheap enough so that we could afford to fly many satellites at the same time in order to get the sampling, the temporal sampling, down to several hours instead of several days, to be able to sample the rapid intensification phase of the storm at the Nyquist rate. So that leads to sort of the mission overview for Cygnus. Again, the motivation or the objective is to penetrate through heavy precipitation to measure wind speed, and also to be able to make measurements often enough to resolve the rapid intensification phase, which equates to making measurements every few hours. All right, and the way we did this, the design of the mission is we have 8 small satellites in a low Earth orbit. They're at a low inclination, 35 degrees. So we don't go any further north or south than 35 degrees latitude, because that's where the storms are. And we use a new type of remote sensing technique, well, new for satellites. It's a biostatic radar, where we use as our transmitting signal the GPS navigation signals that are already there from the GPS satellites. And then each of our satellites carries a modified GPS receiver that's been modified to measure signals reflected off the surface back into space. And this does several things for us. One of them is GPS operates at a very long wavelength, 19-centimeter wavelength, 1600 megahertz, 1.6 gigahertz. So it has no problem at all penetrating through heavy precipitation. And you can see that with GPS receivers that are on your cell phone or that are in a car. When you're using those and it's raining really, really hard, they work just fine because the wavelengths are so long. So we get penetration through the heavy rain because of the signal that we use. And then another nice thing about this technique for remote sensing is GPS receivers it's an extremely mature technology because they're used so commonly in cell phones and cars and airplanes and even satellites. So the electronics have been highly customized or highly optimized for power and size, so that they can be reproduced, and you can build billions of them essentially on cell phones and so on. And what that gives us is these custom ASICs. They're these custom computer or chips that can do all the processing required for very low power, so that they could work on a cell phone without running your battery down. And that lets us install these receivers on very small satellites because they don't require very much power at all. And if the satellites are very small, then they're cheap. And because they're cheap, we can fly a lot of them. And if we fly a lot of them, 8 of them in this case, that gives us the spatial or the temporal sampling that we need to capture the rapid intensification phase of the satellite. So that's the sort of the background on the mission. And I wanted to spend a little bit of time talking about the phenomenology of the remote sensing technique. So the way this works, it's a biostatic radar. The GPS satellites are transmitting all the time, sending their navigation signals down and covering the Earth. And then the Cygnus satellites up here are in orbit looking down at the Earth and looking for the GPS signals. And in general, with radar scattering signals, a signal will go down from a radar, scatter off the surface. With most remote sensing radars, they measure the backscatter signal. So they measure the amount of signal that comes back in the same direction. So the receiver and transmitter are here. But in our case, we're measuring the forward scatter or specular scatter, where the GPS signal goes down. There's a spot here where the signal reflects back up in this direction. And we intentionally tune the satellite to look at the specular reflection point. This is the point where the angle of incidence equals angle of reflection. And the reason for that is the forward specular scattered signal is much, much stronger than the back scattered signal that conventional radars usually measure. The difference in scattering cross-section of the back scatter versus forward scatter is about 30 dB. So the forward scatter signal is about 1,000 times stronger than the back scatter. Because it's so much stronger, that allows us to have a much simpler receiver with a smaller antenna, lower gain, lower noise sensitivity requirements. All kinds of things are much easier on the receiver because the forward scattered signal is 1,000 times stronger than a conventional backscatter. And all of those things add up to allowing us to have a small satellite at low cost so that we can fly many of them. So that's the idea of biostatic specular scattered radar. So the way we measure wind with this is you can think of specular forward scattering. It's a similar phenomena, whether it's at optical wavelengths or microwave wavelengths. So here's an example of specular forward scattering at optical wavelengths. This is just a picture taken of the moon. This is the direct signal, the camera's looking directly at the moon. And then this little moon down here is a specular reflected moon. So the sunlight goes down, hits the lake surface, and then comes up to the camera. And if you look closely at this moon right here, it's almost a circle, right? Just like the moon here. And that's because the water is very, very smooth relative to a wavelength. And if it was perfectly smooth, it would be a perfect mirror reflection, right? And you can actually see, if you look really closely, there's a little bit of roughness around the edges here. And that's because this water surface is not perfectly flat at optical wavelengths, okay? And you could actually, if you analyze this image carefully, you could actually make estimates of the roughness statistics of the oceans, of the lake surface, just from the exact shape on that edge. Okay, so that's what specular reflection looks like at optical wavelengths when the surface is very smooth. When the wind blows, wind roughens the surface of water, and this is an example of wind roughen reflection. So here's the moon again. Here's a roughened surface because the wind has been blowing, and instead of a nice sharp circular moon here, you get this broad region of diffuse scattering, quasi-specular diffuse scattering, and in optics this is called the glistening zone. It's because the water sort of glistens from the reflections, and it's really because all these little facets of water are tilted in different angles, and that causes this partial specular reflection from all these other areas. And the same thing happens if you think of it globally. GPS is scattering off the surface. If the surface is perfectly flat, all your reflections is going to come from that one red spot, the specular point. But when the wind blows, you'll get roughening of the surface, and you'll get this expanded glistening zone around it, and you'll get more and more of the reflections from other places besides the specular point as the wind increases. So if you could image the scattering cross-section of this ocean in the region near the specular point, you could equate that with the degree of roughness of the surface, and from that you could get the local wind speed. And that's exactly how Cygnus works. And this is an example of that. This is a measurement of scattering off the ocean surface of a GPS signal. So this is a GPS navigation signal at 1.6 gigahertz, 19 centimeter wavelength. And it's the specular point in this reflection is right here in the red part, and all this yellow and green around it is diffuse scattering from the glistening zone because the water, or because the air, the wind is blowing and the ocean surface is roughening. So this is a two-dimensional map of the scattering cross-section in the vicinity of the specular point. And these two coordinates here, you can equate these two coordinates to position on the ground in latitude and longitude, but what they actually are, this axis here is the Doppler shift of the signal. So the signal, when it scatters off the surface, gets a different Doppler shift depending on exactly where it is, because of the Doppler is proportional to the component of velocity in the direction of propagation, and that dot product in the direction changes as you move around. So that allows you to isolate different places on the ground by the Doppler shift. So there's a bank of Doppler filters. It's just a FFT processor that processes different Doppler shifts individually. And then this axis here, this CA code shift, that's kind of GPS jargon. It's basically a range gate. So this is the propagation time of the signal. And the propagation time, the time it takes for the signal to go from the GPS to the ground to the receiver, varies as you move around on the surface. The minimum propagation time is at the specular point. That's why this is at the top. And then if you use a longer propagation time, a longer range gate in the radar, you expand out in ellipses that go out away from the specular point. So by varying the range gate in one dimension and the Doppler shift in another dimension, this is all done in an onboard processor in our satellite, you can essentially map out the scattering cross-section of the surface in two dimensions, two spatial dimensions, and from that you can derive the wind speed. All right, and this is an example of how that works. These are measurements. These are called delay Doppler maps. It's a map of the scattering cross-section as a function of time delay and Doppler shift. These are delay Doppler maps for 3 different wind conditions. This is measurements made as we were flying over a buoy, measuring the wind. And as you can see, as the wind gets stronger, the surface gets rougher and the glistening zone expands. The amount of reflection near the specular point goes down. The amount of reflection away from the specular point goes up. And by looking at the behavior of this map, we can estimate the wind speed from the data. And that's exactly what we do with the Cygnus measurements to make wind speed maps. So that's the basic remote sensing phenomenology for Cygnus for as a wind sensor. Okay, so very quickly, this is an expression for the forward model of our measurements. This is an electromagnetic scattering model, and just to give you an idea of what it is we're measuring. So the thing we really want is the scattering cross-section of the surface. That's this thing right here, sigma naught of S. S is just a parameterization of the surface location. This is a two-dimensional integral over the surface of the ocean. This is what we want. This is what we call our level 1 engineering data product, calibrated scattering cross-section. These are the 1 over r squared propagation losses because of the propagation of the electromagnetic signal. This is the response of the time delay filter, the range gating filter. This is the response of the Doppler filter to isolate different spots on the ground. This is our antenna pattern, F of S. You do this integral, and then this is the transmit gain of the GPS, the transmit power of the GPS signal. This is the receive gain of our antenna, the receive antenna. These are some other calibration parameters. All of this stuff together gives us our measurement. This is the receive power as a function of time delay and Doppler shift. So basically, the left-hand side is the actual measurement that we make, and this term right here is what we need to get in order to estimate wind speed, the scattering cross-section versus position. Everything else in this equation are just a bunch of calibration terms that we need to correct for when we calibrate the data. Okay, so this is the input, the raw data measurement. This is the output, the calibrated engineering data from which we get wind. All right, so once we have the scattering cross-section measured, and this is an example of one, we then estimate the wind. And the way that the wind is estimated is we have two different ways of doing that. One of them is you look at the average power in this black box here. This black box is centered on the specular point right here. And as the wind increases, the amount of scattering that's in the box goes down, and more of the signal gets scattered from all these other areas. So this region right here, it's monotonically inversely related to wind speed. Stronger signal, lower wind speed. So that's one way of measuring the wind. And then another way is with the waveform itself. So what this plot here is, it's called the delay waveform. And what you do is you take this plot here, this is scattering cross-section versus Doppler shift in this dimension and time delay in this dimension. And excuse me, you integrate across the Doppler shift, and that gives you a one-dimensional function of time delay. And that's what this plot is here. So excuse me, so it's the received signal as a function of time, basically the radar return pulse. It's just integrate this dimension out and you get a one-dimensional function. And what happens is these different curves are for different wind speeds. As the wind speed grows, the leading edge of this waveform decreases, the slope decreases. So when the ocean's very flat, you get a very sharp vertical return. This red here is very low wind speed, and that's because the surface is very flat and you get this nice sharp return. As the wind blows, the surface gets rougher, and you get some scattering from the very top of the wave and some scattering from the very bottom, the trough of the wave, and the return signal gets smeared out in time. So by looking at the slope of that leading edge, it's also proportional to the wind speed. The higher the wind speed is, the lower the slope. So we have two different ways of measuring the wind speed, and we use both of them in our retrieval algorithm. So that's the way we get wind from the data. Okay, next I've got just a handful of pictures of the hardware to give you an idea of what this looks like. So this is one of the satellites being tested before launch. It's on a little stand. These are solar panels on the top that are folded up. This is the way they're folded up at launch. Solar panels on the front. The science antennas are on the bottom. This is a GPS antenna here for measuring the direct signal for doing navigation, and then the science antennas to measure reflected signal are on the bottom. So that's what it looks like when it was being tested. Here's 4 of the satellites all together. This gives you an idea of how big they are. This is one satellite, another one, and then 2 back here. These 4 are being loaded into a thermal vacuum chamber. This is this great big tube here. It goes inside, we shut the door, pump out all the air, so that it's in a vacuum, and then we cool the whole thing down with liquid nitrogen, so it's very cold, so it seems like it's in outer space, and then we just let it run for about 7 days to make sure that all the hardware can work properly in a vacuum. So this was a thermal vacuum environmental test that was done. And one thing I wanted to point out here is this yellow rectangle right here. That's one of the 2 science antennas that looks down at the ocean surface. It's a 2x3 phase array that looks down to get the reflected GPS signal. And then finally, this is a picture of the satellite, one of the satellites when we were testing the solar panels. So these solar panels are folded up. This is what the solar panels look like when they're opened up. And this is just testing the deployment mechanism to make sure it works. So this gives you, again, an idea of the size of the antenna. Okay, so this is one of the satellites all opened up, and a few key performance characteristics. We have attitude control. We have no propulsion at all. There's no propulsion. We just drift along, and that works fine for us. The total power for the entire satellite is about 38 watts. About 10 watts of this is the GPS receiver. The mass is about 25 kilograms, and you saw the size in that previous picture. Okay, so this is getting ready for launch on the satellite. So this thing here, it's called a deployment module. It's a tube that has little deployment springs on. There's 8 of these little deployment springs. The satellite's attached to each one of these places, and then after launch, they're deployed or pushed out away from the top of the rocket, the 3rd stage of the rocket, into their individual orbit. So this is getting ready to mount the satellites onto this deployment module. And then here's all 8 satellites mounted on the module. This little thing at the bottom is the attachment point that attaches to the top of the rocket. This attaches to the 3rd stage of the rocket. And here's all 8 of our satellites stacked up on top with the solar panels closed, and they're mounted behind these little deployment mechanisms that will push them out into orbit. And this is a test where we took all 8 of them, mounted it on a vibration table, and then we shook it a lot to imitate the vibrations that are experienced when we launch the rocket, to make sure that mechanically everything is built well. And then finally, this is mounting the 8 satellites on the top of the rocket. So the rocket itself is back behind this sheet here, going back that way. It's horizontal, and then these are the 8 satellites being mounted on top of the 3rd stage. And then this is a cowling that goes over the top of the satellite just before we launch. Okay, so this is the rocket mounted on an airplane. So these are small satellites, so we could use a very small rocket. It's called a Pegasus. And this rocket is small enough that we don't need a large first stage. You know, with big rockets and big satellites, you typically have a very large first stage engine that gets you just up out of the lower atmosphere into the stratosphere. And then the first stage falls away and the second stage gets you up further up into space. Because these are so small, what we did instead to save money is we have a smaller rocket that's mounted on the bottom of an airplane, an L-1011 aircraft. Then the airplane flies out. We flew out of Florida, Cape Canaveral Air Force Base, and we flew about 1 hour east over the Atlantic Ocean. And then this airplane just releases the rocket, and it falls away from the airplane for about 5 seconds, and then the engines fire, and it goes up from there. And the airplane is at about 45,000 feet altitude, about like 14 kilometers or so. So it's out of the troposphere up into the lower stratosphere, and it's much cheaper to do it this way if you have a small satellite, or even with, there's 8 small satellites right up here in the front here, and it's still much cheaper to do it this way than using a conventional rocket. Okay, so this is a video when we launched the Cygnus satellites. There was the big airplane that had the rocket on it, and then there was a smaller chase plane that flew along below it just to make sure that everything was healthy before we released the rocket. And the chase plane had a high quality video camera on it that was filming the whole thing. And this is a clip from the chase plane as it was filming the release of the rocket and then the firing to get it into orbit. So I'll play this.
LC, PLT, copy.
LC PEG, PEG is go for launch.
PLT, LC is go for launch. PLT confirm.
LC, PLT, PLT confirms go for launch.
Drop on my mark. 3, 2,
1.
Drop.
Go for release.
Pegasus is away.
And drop. Pegasus is away.
LC, PLT.
Ignition of the Pegasus rocket with Cygnus, helping hurricane forecasters understand and predict the intensity of hurricanes.
Okay, so that was
Chin
the launch.
actuator system.
That was the launch, and it takes about 12 minutes from the launch until you're in orbit, low Earth orbit at 520 kilometers. And after that, after you're in orbit, you wait about 3 minutes to make sure that everything is steady and the rockets have finished burning and so on. And then you release each one of the satellites into their own particular orbit to spread them out around the Earth with that deployment module. So this isn't a video, but it's an artist's conception of the release of the individual satellites into their different orbits. So this is what happened about 15 minutes or 14 minutes after the launch that you just saw in the previous video. Here we go. Right, so they were released in pairs so that the momentum cancels out, so that the third stage doesn't move around too much. And then soon, a few seconds after they're released, the solar panels open up so that the batteries can start charging, and they start orbiting along. And then over a period of a few weeks or a few months, really, each individual satellite settled out into the orbit that we wanted. Okay, and then once they had settled out into the orbits, then we started doing our science measurements, and this gives you an idea of how the science measurements work with the constellation. So this is one of the satellites here, the GPS, the Cygnus satellites, and then these blue ellipses are the specular point reflections from the GPS satellite, and then these ellipses below, these are our antennas, the science antennas looking down at the ocean, and whenever one of these specular points enters into our antenna, the onboard processor acquires it and starts doing all the Doppler shifts and the correlation calculations to measure the reflected power. And that's how we make, measurements. So each Cygnus satellite has 4 GPS receivers to measure 4 different specular points. And that's why there are these 4 different lines coming out of each satellite. And then we have 8 satellites. So there's 8 satellites, each one with 4 channels. And if you add those all together, we're doing 32 different measurements simultaneously of the ocean scattering and the wind. And if you take all of those and piece them together, that gives us our global coverage. So this is what the coverage looks like. Again, you can see a 35-degree inclination orbit. These are measurements made along these lines of all those specular points from the GPS reflection. So that's the way the measurements work. Okay, so this is kind of a summary of what's happened in our post-launch activities. We launched in December 2016. We got the engineering calibrated and commissioned. We started doing science operations in March of 2017. We started releasing data that summer. We got the data calibrated, and our more formal release of data was later in 2017. We reprogrammed our receivers in 2018 because we saw that there was a lot of variations in the GPS transmit power, which were affecting our calibration. So we've corrected those, and now we have a new calibration technique that dynamically monitors the changes in GPS transmit power and does calibration correction. I'll skip over this stuff. So here's some examples of some of the measurements that we've been making with Cygnus. These are measurements of a hurricane, Hurricane Dorian from last year. These are measurements by the whole satellite constellation over 1 hour as it passes by the storm. And you can see the higher red parts of the storm. And this is zooming in on it just over the inner core part of the storm. These are the winds right near the center of the storm. And you can see the times here. We go by this area, we go by a couple times a day, sometimes 3 times a day, depending on the latitude. And yeah, here's a particularly nice one where you can see the structure of the storm, where it's really high winds near the center and the winds die out as you move out away from it. So these are the type of measurements that we're making of the hurricane winds. And now what we've done is taken those hurricane winds and assimilated them into a hurricane forecast model to see how much we can improve the forecasting of hurricane intensity with the data. And this is an example of some of those results. This is the wind speed predicted by the operational hurricane forecast model. This is the wind speed at 3 kilometers altitude, not at the surface, but at 3 kilometers, predicted by the numerical forecast model. This is predicted without Cygnus, and this is predicted with the Cygnus data added. And you can see that when you add the Cygnus data, the peak winds shift from here. The peak winds are due north of the storm, and here the peak winds shift off to the northeast. And the reason is we're better able to monitor the latent heat flux of the evaporation off the surface, so we can track where the energy is that's forcing the higher altitude winds. And the reason we picked this particular product, the 3-kilometer altitude wind, is because there was one of those Hurricane Hunter airplanes that flew through this storm at just this time, and it was making measurements of the wind at 3 kilometers. And these are the measurements that were made by the airplane. And you can see it has this same asymmetric behavior off to the northeast that was captured by the forecast model using the Cygnus wind. So that's a good indication that we have, we're adding valuable information about the latent heat flux and the energy and evolution of the storm with the Cygnus winds. And this is one other example of that. This is estimating the minimum pressure in the storm, which is a proxy for the strength of the storm. And this red line is the estimate of the minimum pressure estimated by the operational forecast model, the National Hurricanes Forecast Model. This black line is the actual true pressure that actually happened. And this sudden pressure drop right here, this was the rapid intensification phase for Hurricane Michael, and the intensification was almost completely missed. There's a little bit of a dip here, but it didn't get anywhere near deep as actually happened. This is a typical example of a storm forecast that missed a rapid intensification. This is the control when we use the standard operational forecast model, and this is the same model when we add the Cygnus data in, and you can see that we do a better job of tracking in the red here the deep intensification or the decrease in the minimum pressure when you include information about the surface wind. So that's a good indication. Okay, I wanted to shift gears here in the last few slides here and talk a little bit about other things that we're using Cygnus data for besides hurricane winds. So Cygnus is running all the time when it's in orbit, and it's taking data whether you're over land or over the ocean. And in particular, when you're over land, we're measuring scattering cross sections off the land surface, and there's a lot of valuable information that we can get about the scattering from the land. And this is an example of some early images that we made of Cygnus over land. And I'm going to show you 3 different examples of the same section of the Amazon River. So this is actually in Brazil. This is measurements made by 3 different sensors that all operate at nearly the same microwave frequency. So this first one is a measurement made by the SMAP passive microwave instrument. This is a NASA satellite that has a radiometer that operates at 1.4 gigahertz, so almost the same wavelength of frequency as Cygnus, but it has a 30-kilometer resolution. And this is an image of a major section of the Amazon River with 30-kilometer resolution imaged at microwave frequencies, 1.4 gigahertz. So there's another instrument on the same satellite, SMAP. It's a radar that operates at 1.2 gigahertz, almost the same frequency, and it has about 3-kilometer resolution, so 10 times better resolution. And this is that same section of the river. And you can see much finer resolution. The spatial resolution is better. You can pick up some of the small scale tributaries feeding into the river that you can kind of see here, but not so much. And in any event, you can see that this has much better spatial resolution. So this is 3 kilometers from SMAP radar, 3 kilometers from SMAP passive microwave. And then we imaged the exact same section with Cygnus, and this is what we got. So you can see the spatial resolution with the Cygnus measurements is much, much higher than with either the radar or the radiometer, much lower than 3-kilometer resolution. And this was actually a pleasant surprise. We weren't expecting to see this kind of quality resolution in the forward specular direction. And it's because of this image and some others like it early on in the mission that we've refocused a lot of energy in the mission, or added people to the mission to look at the land data because of the extra things that it can do for us. The reason why the resolution is so much higher than those other techniques over land has to do with the difference between incoherent and coherent scattering. So incoherent scattering happens over the open ocean where the surface is rough, and here's the GPS transmitter, here's the Cygnus receiver, and the signal goes down, it illuminates the surface. And if the surface is rough relative to a wavelength, then every little spot on the ground you can think of as an independent radiator with no phase coherence. And the signal that's measured here ends up being proportional to 1 over r squared for this distance times 1 over r squared for this distance. And you just add the powers incoherently because the surface is so rough. If the surface is really smooth, which is what happens with inland water, like a river or a lake, the surface is much, much smoother than the ocean. And what happens is you get specular reflection, and the dependence on range goes as 1 over the sum of the square of the sum of the ranges. This form here, as opposed to this form, the dependence on range is critical, because if you actually plug in the numbers for the range with Cygnus and the range with GPS, the difference between this dependence on range and this dependence on range is about 30 dB. It's actually more like 33, 34 dB. So what that means is the scattered signal from calm water, smooth water, is about 2,000 to 5,000 times stronger than the reflections from the ocean. It's really, really huge. And that's the reason why we can detect these tiny little water features, like these little features that are much, much smaller than a kilometer, stand out because the scattering from the calm water is thousands of times stronger than it is from the ocean, or from the land around it, for that matter. So that's it's a really excellent quality, dependence that we can leverage. And an example of that are some land measurements that we made of a hurricane after it made landfall. This is Hurricane Harvey, which caused a lot of flooding in southeast Texas. This is the land image by Cygnus just before landfall, and this is the land in the days after the hurricane made landfall. And you can see this area getting redder and redder and redder, and that's because of all the standing water from flooding. And one other example of that is this image, these pair of images here. There was a huge flooding event that happened in November 2018 in northwestern Iraq. And these are images made by Cygnus. This is made before the flooding event, and this is just after the flooding. And this region right up in here in northwestern Iraq, right in here, you can see the color changes quite a bit to from kind of reds to greens and yellows. And this is all from standing water from the flooding. So this is it's a new technique, a new capability that we're just starting to really leverage, the ability to do high resolution images of inland waterways. And let me just skip ahead here. I'll get just one last thing here, just as a summary of what Cygnus has done and is doing. So we launched in December 2016. All 8 spacecraft are on orbit now, taking data 24/7. We're getting lots of data over ocean and land. Over ocean, we're making routine measurements of winds in hurricanes and taking the wind data and assimilating them into forecast models to work on improving tropical cyclone or hurricane forecast skill, especially for intensity. And over land, we have this ability to do high resolution measurements of inland water, and we're using that to do things like imaging waterways and imaging flood inundation after major storms. And these are the 2 main areas that we'll be working on in the future with Cygnus. And I think I'll stop here. So thank you very much. Hello?
Okay. Thank you, Chris.
Yes.
It was a very nice and quite interesting presentation. It's quite nice to see what we is discovering how to work with GPS, because GPS was developed for positioning, navigation, and now we can use GPS for several applications. It's a multi-purpose system. It is quite interesting. Of course, that a lot of questions will rise, but first I'd like to pass to Felipe Nivinski to make some initial consideration. Hello, Felipe.
Hello, can you hear me okay?
Yes.
Yes.
Well, thank you, Chris, for the excellent presentation. Just the launch was such an epic feat that I'm sure it for a lot of our students it will keep in their minds for much time.
Yeah, the launch was an exciting day.
Yes.
Actually, the most exciting, there was 5 seconds after the rocket was released from the airplane and before the engine fires is about 5 seconds, and everybody's very, very nervous.
Yes, I can imagine. And in the end, science worked, right?
Yes.
So that's great. Well, we will be taking questions from the audience, and I made a few here. And we're trying to make this more for students to get into GNSS reflectometry.
Okay.
So if you had any suggestions or thoughts on how graduate students in remote sensing fields could get started on GNSSR, what would you recommend?
Well, first of all, the data from the Cygnus mission is all publicly available. Anybody can access all of our data. It's very easy to find. It's on a NASA data server. So if you have an interest in working with the data, it's readily available, and there's lots of documentation about how to use the data and how it's calibrated, and some example software for opening the files and reading them and so on. So that part of it we've tried to make as easy as possible for anyone who's curious and interested. As far as what to do with the data, there's this is a pretty new technique, the GNSSR remote sensing. It's quite new, so there's lots of things that are still not known about how to use the data, the possible science applications, and also the engineering side of how to calibrate the data and how to interpret it. So yeah, there's many questions and new areas, I think more so than with most traditional remote sensing techniques that are more mature and have been around for 20 or 30 years, where there's still a lot of sort of second order corrections to make it better. But with GNSSR, there's still some first order unanswered questions. Even like the measurements over of the water over land, we don't really understand what the spatial resolution is. Maybe it's 10 meters, maybe it's 50 meters. It's not clear. But even that, as an image processing question or signal processing question, understanding what the true native resolution of the measurements is, that's an open engineering question.
Yes, you are on the diffraction limit right there, right?
Well, it's beyond the diffraction limit. Actually, it's quite a way beyond. It really, the reason the spatial resolution is so good, I mean, it relies on the Fresnel zone of the reflections. So it's the phase interference of the different reflecting terms. Yeah, our antennas are very small. I mean, the diffraction limit for our antennas is several hundred kilometers, actually.
Mm-hmm.
So yeah, the resolution of 10 meters or 50 meters, it's a different phenomenon. And yeah, and it's not clear actually what the resolution is, but the pictures are very nice. So it's obviously good. Yeah.
It works very well.
About the interference of the ionosphere and the troposphere, does it make any problem for the analysis or not?
It depends on the application. So there's some people on the science team that are working on altimetry, using the data for altimetry, because you can time the signal, the GPS signal, and the time of, the propagation time. And from that, you can get the sea level. And with those measurements, the propagation time is changed by the, the integrated electron content of the ionosphere, right? Because it changes the refractivity. And you need to know that in order to get an absolute measurement of the sea level. So that's a concern with these measurements, that there's an unknown offset due to the ionosphere. For most of the measurements we make, we're interested in the power of the scattering, not the timing for the wind measurements. And then we don't need to know the propagation time.
Okay, let me invite Chris Line to make a question. She has a question.
Yes.
Okay. Thank you, Chris, for the nice talk. I have a question.
Yes.
Some Cygnus parameters aren't well estimated, such as the receiver gain, GPS transmitter power, and transmitter and receiver ranges to the specular points. How does it affect the quality of Cygnus measurements and results, and what are our plans to improve the quality of the observations?
Right. So we have estimates for all of those parameters. Some of them are better and some of them are worse. So there's still room for improvement. But I'll mention a few of them. As I said during the talk, the amplitude of the GPS transmit signal needs to be known. And when we first launched Cygnus, we thought that the GPS transmit power would be fairly constant over time, and we were wrong. It actually changes quite a bit, and it changes over very short time periods, tens of seconds, and it's because of the the government control of the GPS constellation is by the United States Air Force, the military. And they have other applications for GPS, of course, that are not civilian science applications. So they change their power and they turn it up and they turn it down and they move around the different sidebands depending on what part of the world they're over. Some parts of the world, they have a lot more problems with interactions with other jamming and things like that, interference. So they turn the power up or they turn it down. So we have to compensate for that. And what we did in the second year on orbit, when we started seeing this problem in our science data, we reprogrammed the navigation receiver. We have a GPS navigation receiver that's not for science. It's just to do location of the satellite, conventional GPS. We reprogrammed that so that it could also measure the power of the transmitted signal, the GPS transmit signal. And we now use that to calibrate the science data. It wasn't something we were planning to do, but that's what we're doing now. And that seems to be working okay. And then as far as the receiver gain, the recalibration of the receiver characteristics, we make measurements of the, I showed those delayed Doppler maps of the scattering from the ocean surface, and the part where you can see the ocean, that's where our science data is. But we also have measurements that are far away from the specular point, where there's no scattered power. And we also make measurements there, and that's the noise floor of the measurement. And that tells us the receiver gain and the changes in the receiver properties, and that's factored into our calibration equation.
Hello, Chris. We have some question from the audience.
Yes.
One of them is this system better than Japanese airborne TRMM?
Better. No, it's different. The Japanese TRMM operates at a higher frequency, lower wavelength. So they have trouble penetrating through rain, especially heavy rain. So for applications where you're trying to make surface measurements under heavy rain, Cygnus has an advantage. Okay, but if you're interested in measuring the rain, like TRMM, it's a precipitation mission. So they actually want to have interaction with the rain. So they're able to make measurements of the atmosphere, which we can't make measurements of the atmosphere at all with Cygnus because the wavelength is so long that there's no significant interaction with rain or cloud. So yeah, TRIM is optimized as an atmospheric science mission, and we're optimized as a surface imaging mission.
Thank you.
Yeah.
Could you make the next question, Felipe, that is on the screen?
Yes, sure. So again from YouTube, what are, in your view, the main challenges in soil moisture estimation using this type of observations?
In soil moisture, I think, so there are a number of groups on the Cygnus science team who are investigating soil moisture retrieval. There's been a series of papers that have started coming out in the last 2 years. And so, the first order answer is we're able to measure soil moisture, and it's approximately comparable to the SMAP soil moisture measurement. There are secondary influences on the measurement that need to be corrected, and those are really the challenges. The main one is the sensitivity to the surface roughness conditions. Because the roughness has a strong impact on our scattering cross-section. I mean, that's why we can measure the wind, is because we're sensitive to the roughness. So if we're interested in soil moisture, we don't want the roughness of the surface to influence our soil moisture measurement, and it has a direct influence on the strength of the signal. So there needs to be some way to correct for or compensate for the horizontal, the non-uniform variations in roughness that are not caused by soil moisture. That's probably the main concern right now.
Just to remove the topography from the
right. That's right. So a common way to address this with SMAP, which is something that we're going to try, is once you have a full year of data, so you can look at the full annual cycle, you can customize the retrieval in every pixel, so that you come up with a history for that particular pixel, and you have some kind of a roughness map that you can use as to calibrate the algorithm individually. So it's something like that is what we're looking at.
Thank you, Chris. Chris Lane, could you make the next one?
Sure. From YouTube, do you foresee any application of this technology in precision agriculture, such as in detection of insect clouds?
I'm sorry, in the detection of what?
Insect clouds.
Insect clouds.
Insect clouds. Well, we won't see insects scattering in the air, I don't think. I mean, the density of those is small, and also they're generally small. Well, actually, I guess in Brazil you have some insects that are as big as our wavelength, maybe, but not here, not in the U.S. The insects are smaller. But there's actually one related application, a new Cygnus application, which is really pretty interesting, related to insects. This is work that's being done together with the NASA Cygnus team, some other groups at NASA, working with United Nations. It's the Agriculture AOR, I forget. It's a United Nations organization that works with agricultural support in Africa. So they're working with the Cygnus team, and it's using our soil moisture product. So one nice thing about the Cygnus soil moisture product is it's able to penetrate through heavy vegetation and still give good soil moisture measurements under a thick vegetation canopy. Because the wavelength is long enough, it can penetrate through the wet leaves. There's a certain combination of conditions when you have a lot of soil moisture, you have a moist soil and you have a thick vegetation canopy above it. That combination is very conducive to supporting locust outbreaks, because locusts, there's a big locust problem right now in East Africa. And locusts, when the eggs first hatch, there's a period of about 3 weeks when they can't fly yet. So when they first hatch, the soil has to be moist to support the eggs. And then after they hatch, there has to be a lot of vegetation that's right nearby, because they can't fly. So they have to be able to crawl up the trees or whatever to get to the leaves. And then after about 3 weeks, they can fly, and then they dissipate, and it's much harder to control. So they're working with the Cygnus team on isolating these locations with a combination of high soil moisture, high vegetation, and then they are going out to these sites with some eradication. I don't know if it's like spraying poison or something to try to eradicate them before they can start to fly. So that's actually a really exciting application that it's just getting started now, working together with the United Nations organization in Africa. So it's related to insects, but not once they're airborne, they're not really visible in our data.
Yeah, thank you. We have another question here. Is there a possibility to analyze floods in urban areas?
Oh yeah, that's actually a very active part of what we're doing, because the spatial resolution is quite high, tens of meters apparently, and so we can see the motion of the floodwaters. It's like after a major precipitation event from rain in rivers, or with hurricane landfalls that cause floods. Either way, we can see those changes, and because we have so many satellites, we get new measurements 2 or 3 times a day. So you can see the dynamics of the flood moving from day to day. And so there's work going on taking those measurements and using them as validation for hydrological flood models, that try to predict where the floods are going to go, and using this data as validation. So yeah, that's actually it's an active part of our study right now.
Felipe, could you read the next one?
Yes, I had one of my own actually. I'll do that first. So you mentioned about altimetry applications, and what's your opinion on near grazing incidents and the trade-offs with occultation and reflectometry?
Right. Well, the near grazing is actually, I think, the much more exciting possibility for GNSSR. And the reason is, I don't know if you're familiar with the difference between carrier phase delay and group delay altimetry, those two things. So, the traditional radar altimeters like Jason or Topex, they use group delay altimetry where you send out a pulse and then you time it and you measure when it comes back, right? That's the traditional group delay altimetry. And that works fine with the specialized radar altimeter missions, because the pulses have very wide bandwidth, so they have very good vertical resolution and height resolution for the sea height, right? But with GNSSR, the bandwidth is quite low. It's only about 4 megahertz, the GPS bandwidth, as opposed to about 350 megahertz for JSON. So it's much poorer vertical resolution. It's of order 3 to 5 meters vertical resolution. So it's not really useful for any high precision satellite altimetry for oceanography. But carrier phase altimetry is completely different. It looks at the phase of the carrier, the 1600 megahertz carrier, and looks at changes in the phase to resolve the height. And with those, it's proportional to the wavelength. Our wavelength is 19 centimeters. That's one wavelength. So if you can resolve the phase to 30 or 45 degrees, that means your resolution is about 1/8 of a wavelength, a few centimeters. And that is the right order to be able to do precision altimetry. The problem is you can only do carrier phase altimetry if the surface is flat enough to give you clean specular reflections where you can still see the phase of the reflected signal. And that happens almost only at grazing angles, because the surface roughness, what matters is the projected roughness in the direction of propagation, not the vertical roughness. So the ocean has a certain roughness scale, tens of centimeters or more, but when you look at a grazing angle, the effective roughness goes down by the secant of the angle right? So you can do a lot of carrier phase altimetry with Cygnus at grazing angles. That's been demonstrated. And then you have the potential for doing, centimeter scale altimetry. And how that relates to radio occultation, I think the main way it relates is, in order to optimize the instrument design to work well at grazing angles, it's, in terms of the antenna positioning and the polarization of the antenna, it's almost identical to the way you optimize for radio occultation. So there's a natural complementarity where you could do both of those science goals with the same hardware.
Oh, that's great.
Yeah.
We have here a question from Murilo da Silva. Is there an estimate of how many lives can be saved with this system?
How many lives? Oh, I don't know. I don't know. I don't know. I don't know the answer to that. I hope the answer is many.
Felipe, any more question? Chris Line?
Chris?
I have one more.
Yes.
Yes. Each signal satellite has 4 channels and therefore can measure 4 simultaneous reflections at a time. So I'm sure that many other reflections reach the satellite antenna. So how do the satellite instruments select which observation will be processed? And do you have any plans to improve the satellite's capability in terms of the number of observations?
Right. Okay. So there's an onboard processor on each satellite that has a list of all the GPS satellites that are available, right? And it calculates where the specular points are for each one. There's usually between 6 and 10 possible specular points that it can see at any given time. And it looks at each one of them and where they are on the ground, and in particular, where they are in the Cygnus antenna pattern. And it selects the 4 that have the highest antenna pattern gain. Those will give us the strongest signals. So it's constantly doing that selection algorithm all the time and choosing which ones to use. Okay, so that's the way the current one works. There's a new Cygnus receiver development effort. It started about 4 years ago, and it's actually just finishing now. We have a new receiver that we've developed that has more modern electronics, better gate array. It can handle about 20 channels simultaneously, and it can also handle both GPS and Galileo, the European GNSS, and Beidou, the Chinese one, and GLONASS, the Russian one. So it has all those channels included in its capability. Plus, it's just a bigger processor, so it can do 20 simultaneously, and it'll have a similar sort of algorithm to look at all the different possibilities and choose the ones to assess. And that instrument, it's going through its final laboratory testing right now. It's here in Michigan, and we have plans in next May, hopefully, if the COVID thing starts to go away. We have plans. We're collaborating with the New Zealand Space Agency right now, and Air New Zealand, the commercial airline in New Zealand, where they're going to let us install one of our instruments on one of their airplanes permanently. So it'll be on an Air New Zealand airplane flying all the time, and we'll have an automatic link through a cell phone from this airplane to the ground at the University of Auckland, and then from there through the internet to Michigan, to collect lots of data with this new instrument to test out the operation and make sure it's working okay. And also it'll be going, the northern part of New Zealand is inside of the Cygnus coverage, because Cygnus can only go to about 39 degrees south latitude. So there's a little bit of overlap with northern New Zealand. So we'll also have some intercalibration with Cygnus. And this will be a way for us to test out all the new capabilities of the new receiver. And then eventually we want to try to get it on a new satellite mission. But that's not confirmed yet. That's just a hope.
Okay, thank you. Felipe, any final comments? The time is fly quite quickly.
Yeah, I think it's about time to finish. I just had one quick question. How far do you see us from a commercial sector exploitation?
It's kind of already happening. I mean, there's a company, Spire. The company Spire, they have launched 2 GNSSR satellites already. They're up there now, and they're still doing their testing and demonstrating the technology and so on, and starting to do some science, wind measurements and soil moisture measurements. They've started doing that. And I know the people at the company very well. Actually, some of them used to be part of the Cygnus team, but then this private company offered them more money or something. So now they're doing the private version. And so they, the senior management of that company believes that this is a reasonable business investment to try to do GNSSR satellites and then sell the data. I guess they want to sell the data. I'm not sure what the business model is, but this is something that they're investing in as a private investment. So maybe it's already happening.
Okay, thank you very much. You have to close this session.
Okay.
I'd like to say thank you very much, Chris. It was a very nice presentation, very nice discussion. Thank you, Felipe Nivinsky, for taking part of this talk here together with Chris Lane. It was a big pleasure to stay with you. Thank you very much.
All right, thank you. Yeah, it was my pleasure. I enjoyed it very much. Maybe next time I'll visit Brazil for a talk.
You have to. You are invited. Once this pandemic finish, you are welcome to visit us.
Thank you.
Thank you, Chris.
Okay. Bye-bye.
Bye-bye.
Thank you. Bye. Bye. Thank you.
Bye-bye.